Our body is made up of what percentage of fluid, by the way? Yeah, around 70. Oh, 90%. Yeah, 70s. It depends on, I guess, who is hydrated versus not so hydrated, right? But I think, anyway, so a lot of percent, there is a lot of fluid inside our body. So how the fluid moves inside our body is governed by the rules we're going to be talking in this chapter, okay? So it's going to come out handy, okay? Hey, now we have detailed information. But for me, all I need is there is a lot of fluid inside our body, okay? So that's all I need to know. So exact percent is not of that much interest for me for this class here, okay? So anyway, thank you for the feedback, those wonderful feedbacks there. Okay, so whatever rules we're gonna be learning here about the fluids, we can use that and apply to the fluids that's inside our body as well, okay? And it seems like Sila is adding more fluids. Okay. Okay, so now what's the difference between solid, liquid, and fluid? So we know if the ice, we call it solid, and if we warm it, it becomes water. And if we keep on warming it until it starts boiling, what happens? Same water becomes now vapor. So they are related. Only difference is that how tightly the molecules are binding each other, how they are, how strong the force between those two molecules are, okay? So solid, the forces are strong. So what happens is molecules, they cannot slide or move. But in case of liquid, what happens? They cannot move far apart from each other, but they can slide around. And because of that, they can change their shape to the shape of the container because they can slide around and change the shape. Oh, gas, oh, they can fly around. So the distance between molecule is far, can be way far, okay? See here, distance is not much difference compared to the solid. Only difference is now force is smaller. Because of that, they can slide around. Here, they can fly around, not just slide around, but they can fly around. We know that, right? So the liquid and gas, they are called, collectively, they are known as fluid. Okay. So one more difference, one main difference between liquid and gas is that since the molecules are already close together, we cannot push them further closer. So liquids are not that much compressible. But since the gas molecules being far apart, we can compress, okay, them and bring them closer. So for example, you fill the air, you fill the balloon with the air, and if you are careful, then you can keep on squeezing and make the volume smaller, means now these gas molecules, same number of gas molecules, they are now closer, okay? So how do these gas and liquid behave? We're gonna be talking about in this chapter and the next chapter. So gas law, and the fluid, the law we're going to be talking here, are going to apply for mostly for both gas and the liquid, both fluids, okay? So now, what happens is when we're talking about fluids, rather than talking in terms of mass, we may talk in terms of density. And density is defined as mass divided by volume. okay? Mass divided by volume. So now, here is this information here. So there is 1 cube and now there is another bigger cube. So the length of this side is exactly double, and being cube, this is also 2L, right? And this is also 2L. So now question is, which has a greater density? Remember, this has mass m, and this whole thing has mass 4 times m, okay? So now, how about density? So think about it. Use this formula for the guidance and respond to this. And you have, let's say, 1.5 minutes to answer this question, okay? Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. Okay, mostly A, but there are B and C as well. So I see Robert has some response on the chat. Looks like that's going to be helpful. So density of A is mass of A divided by volume of A. So what is mass of A? Mass of A is M. How about volume of A? This is L, so that means it's going to be L cubed. Okay. So that's the density of A. How about density of B then? Mass is 4 times mass of A, or I should write 4 times M. Volume is 2L cubed, right? So what do we get here? 4M over 8L cube. So M over L cube, M over L cube. So it has a density difference by this factor here, which is half, okay? So it looks like B has a smaller density. A has a larger density, okay? So what happens here? It's packing more mass, the same volume here, compared to this one there, okay? So that's what's happening. So if it can pack more mass in the same volume, that means it's going to have more density. So you may be thinking, okay, there is just M, this is 4 times. Yes, mass is 4 times, but volume is, this volume is 8 times larger, see? 2 cubed means 8. Okay. Okay. Did I choose the answer? Nope. That's the answer. Are they made up of same material? So let me make this clicker question. A, yes. B, no. You have 30 seconds to respond. 30 seconds, folks. Five more seconds. 5, 4, 3, 2, 1, and it starts. Okay, so if I'm thinking B as the correct answer, am I right? And why?
Well, I said that that they were made of the same material just because the mass M value is the same between the two.
They are made up of same material because mass and value are same? Volume are same?
That's what I had put
Okay.
together as why they were the same.
Okay, so it looks like B is not the right answer then. And I see on the screen, since they have different densities, they are made up of same, and a lot of people are pointing towards that. So I'm kind of losing that. Okay. So this is property of material. So what happens is if we know density, and that means one kind of material have one density, same density. So for example, we may have, let's say, iron ball or iron block or iron rod. All of them have same density. That's what we know. They may have different mass, different volume, but when we gather mass and divide that mass by the volume, we get same density. Okay, and so density is the property of the material. Okay, so if we know density is same, that means it's the same material. Okay, so different materials, they have different densities. So I think I went a little ahead and asked this question without talking about it. Okay, so for this I'm giving credit to everybody. So density, same density means same material. If they are different density means they are not same materials. Okay, so now what happens is density is not just the mass or not just the volume. Okay, it's the combination of both. So what happens? For example, let's take a look. If I put a balloon full of air, a balloon, regular size balloon, I don't know, maybe this big balloon, okay? If I put air, so this is volume of this balloon. Volume is fixed. Let's say we just putting that much air and we get this much volume. So that's going to give me a density. To find density, I need to know how much mass I put in. Let's suppose somehow I know how much air I put in there, right? So now if I were to put, let's say, iron block inside it, and this balloon is some sort of magic kind of balloon that does not tear up so quickly, okay? So let's say I put some iron dust and fill to the same volume. What's going to happen? It's going to be a lot heavier, mass is larger. So mass is going to be larger than the mass of the air for the same volume. So that means iron has larger density, okay? So anyway, so density gonna come out handy. So if we understand what density means, okay, it's gonna be easier for us to study the properties of these materials there. So this is one property. Density is one property of materials. Another property can be, oh, it says more about the density. So that's what I was talking about, okay? So for example, when we say water, water has about 1,000 kilogram per cubic meter, okay? Air has only that much. So what does it mean, kilogram per cubic meter? So cubic meter is a volume, right? So if, let's say for convenience, if we make length 1 meter, or you may say width, okay? This is also 1 meter. Hey, this is not cube, that's a square. How do I make cube? Okay, so that is also 1 meter. So let's suppose I have a container like this. That means I can tell this is 1 cubic meter. But of course, this can be larger and this can be shorter and so on, as long as combination of the product of this and that is 1, still volume is 1 cubic meter. Now let's say if I put water full of this container that has a volume of 1 cubic meter, then how much mass is going to be there? 1,000 kilogram. But if I put just air, then this is going to be just 1.28. So density of air is way smaller, nearly 1,000 times smaller. Not 1,000, maybe 800, 700, right? And blood has a density slightly larger than the density of water because blood has some mineral in it. And minerals, they are a bit heavier than the water, we know, right? And another thing we're going to be frequently talking in this class going to be the mercury. Mercury is fluid, but it has the highest density among any other fluid, okay? Very large density. So density may be also given in terms of specific gravity. So although the name is a specific gravity, it has nothing to do with gravity though, okay? So if we divide density of anything by density of water, which is 1,000 kilogram per cubic meter, then what happens? We call that specific gravity. By doing that, what are we doing is, let's say the object is blood. Density of blood is 1050 and density of water is 1,000, and both of them have same unit. Means this and that gonna cancel, giving us just a number. So it's saying blood has a specific gravity slightly larger than 1. What it means? It means it has a density slightly larger than density of water. By writing a specific gravity, we are writing this number and writing density compared to the density of water. So that's what we are doing. So when we have a nice pure number like this, it becomes easier to table it, right? So for example, density of blood on the table there. And then you write specific gravity or density. You can write 1.050. And if you want that of mercury, looks like my table doesn't look very good here for the blood, let's say, and for the mercury, it's gonna be what? 13.6. See, you get just pure number. And not so long ago, we did not have internet. And we had to keep track of all these numbers by making tables and putting that in a book. So to minimize the spacey text, there was this kind of practice. Okay, so now what it means for this class is, if you are given specific gravity, that means you are given density in Dirac. You just multiply that specific gravity by density of water, and that's going to be the density of the object. Okay, multiply specific gravity by density of water, and which is easier to do because it's 1000. Multiplying by a number with a bunch of just zero, it's easier, right? So we can easily find it, right? So when it says specific gravity of blood is 1.050, that means density gonna be this number here times 1000. Okay, that's it. That's all we need for this class. So sometimes you may be given specific gravity rather than density directly. So in that case, you convert that specific gravity into, okay, the blood of friendship is thicker than the waters of birth. Okay, so is that some famous quote from somebody? I guess I haven't.
No, that's a translation of the original quote. The blood of the covenant is thicker than the waters of the womb.
Oh.
The mainstream saying is blood is thicker than water, as if to denote family is better than your friendships, but the original saying was trying to say that your friendships are worth more than your family.
Oh, I see now. Thank you for that. So now there is another property of fluid we're going to be using a lot. That's a pressure. Okay. And we are kind of familiar with pressure thingy, but here I like to point out, where does the pressure come from? When we say something has a pressure, what does it mean? Okay. So everything has this mass, and for example, these mass, the matter, they are made up of molecules or atoms, right? And for example, for the gas, what happens? These atoms or molecules, they are free to move. So when they are free to move, and when we put that inside a case or container, right, what happens? It's going to bounce back and forth. So when it does, it hits the side of the container. Okay, so that's what it does. So it's heating. It hits. So let's think in terms of momentum change. So these things have mass, right? And mass times velocity means momentum. So when momentum changes, there is force associated with it, right? Force associated with it. So that force divided by that area gives you the pressure. Okay, so that's what's happening inside the tire. So you pump air inside. What happens? They are bouncing around. By doing that, they are interacting with the wall and interacting with each other as well, but not as much. They interact with the wall of this tire. So if you can figure out how much average force they are exerting and divide by the area, then you're going to get the pressure on this side. But of course, the pressure is going to be same all around or all over this tire. Okay. So unit of pressure is unit of force, which is Newton, divided by unit of area, which is meter times meter, meter squared, right? And this is also called Pascal. That's the name from a scientist. We'll learn about Pascal's law regarding pressure, okay? So 1 Newton meter square is 1 Pascal. But of course, there are other units as well, but these are the SI unit. But there are other units. For example, we may say atmospheric pressure and blood pressure. When I say my blood pressure is 100, around 100, what unit I'm using? That definitely not Newton over a square meter or Pascal. It's not, okay? We are using different unit, and you will be surprised that's not even the unit of pressure. Actually, it's something else, and we'll learn about that, okay? But 1 atmospheric pressure is about 10 to the power 5 Newton square meter or Pascal, okay? Slightly larger than that. And of course, tire pressure we measure in terms of PSI. So that means pound per square inch. So per square inch is area in different unit, right? And pound is the force in different unit. So now here is this question where many students get it wrong. So I'm warning you, so pay a lot of attention here and answer this. And you have 2 minutes to answer this question. And 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. So let's suppose I'm thinking A as the correct answer. Am I right or wrong, and why?
I think A is the correct answer because the pressure is 12 pounds per square inch in the space station. It's always going to be the same, isn't it?
So it does not depend on the area?
You know, I'm not sure. No, it doesn't depend on the area. It doesn't depend on the area at all.
So how about the area? The formula has an area in it.
Uh-huh. So I'm thinking, okay, if there's an area in the formula, and I know that an area is something multiplied by something else, you know, one side times another side. Okay, sure. Then maybe, yes, there's the formula right there. Okay. Well, I have a force divided by an area. Okay. And that gives us the average pressure. And the average pressure
Did I
in
confuse you?
and the average pressure in the space station is 12 pounds per square inch. So we already know the end product of the formula. We know that it's 12 pounds per square inch because that's the average pressure. So there's the average pressure.
So this question is giving you area, just like I think it's Brittany, right? Who recently wrote in the chat. Pressure is same for both because it's just 12 psi. It's a given. And so you were right in first place, Robert. So
What
I
do you
just
mean?
confused you. I simply confused you.
Oh, no. I picked C. I was trying to argue for A.
Oh. So
No, I actually picked C, but I was arguing for A because I thought it was wrong. So I tried to work my way through it.
Okay.
So yay.
Hopefully
Fun.
this discussion helped them.
It
Okay.
did. It did.
So inside this room, pressure is same, right? When we say atmospheric pressure, about same, right? So pressure is given already, and you are asked question about the pressure. So it's it may seem like a bit tricky. So what is different in this case is the force on these windows. Force on these windows is going to be different. Now pressure is same. Area is different, means force acting on those windows is going to be different. Okay. So let's watch this brief video here.
So here we've got a 50-liter glass jug of water. I'm going to try to break this using just this amount of water. Who is a little bit skeptical? Oh, I know there's some skeptics in the crowd. Okay. How many people here believe that this is going, like really believe that this is going to work?
We have faith in physics.
Let's see who wins, Katerina or the barrel? But wait, how did such a small amount of water break such a large barrel? Let's go back to the beginning to understand this. So what is hydrostatic pressure? You know how when you dive into a swimming pool or the ocean and you go deep and you feel pressure in your ears pushing your eardrums? As you go deeper, you feel more and more pressure in your ear. And that's pretty intuitive, right? The deeper you go, the more pressure. And when I teach pressure in my class, my students have no trouble understanding the correlation between depth, or another way to think about it is the height of the water above you when you're diving. More height, more pressure. But what they do have trouble really understanding and grasping and believing is that the height is the only thing that affects the pressure. Think about the Hoover Dam. They build a huge thick wall there to block the water from falling. That's not because Lake Mead behind it has so much water in it, which is pushing with a huge mass of water. In fact, if you took away Lake Mead completely and kept only a thin film of water right where the dam is, going as deep as the dam, you would feel the same pressure as with a whole lake. And another example is if you had a long, thin straw extending 150 feet, the pressure at the bottom of the straw would be the same as if you dove in the ocean 150 feet deep. Glass jug of water, and it's already full, as you can see. And on top of that, we have a hose that extends the 155 feet up into the top of Fine Hall. When the pressure of the water goes down, it pushes down on top of the liquid, right? But that pressure is then evenly distributed throughout the whole volume of the water. So the entire jug will feel that same pressure. And in particular, every point on the surface of the glass
will also feel that pressure. So it's basically we're channeling the pressure from this hose throughout the entire glass, and if we reach a high enough pressure, in theory, it should shatter.
Notice how it starts breaking all points, okay? Everywhere, it starts breaking from everywhere. That means pressure is acting every point, everywhere. Not just at one point, but everywhere. Cool, huh? So pressure simply depends on height. One thing to remember. Another thing is that pressure acts equally in all directions. As we saw, this thing started breaking from all points same time. Okay, so two things, main thing we want to get out of here.
So here we've got.
Okay, so now let's come back to our bathroom. Okay, so if you have a toothpaste, you know, in a tube, you don't need to squeeze near the hole. You can squeeze anywhere. And what happens? The toothpaste comes out. So you are applying force here over that area, means you are applying pressure over there, and that gets transmitted all over, pushing this one out, right? And since we already watched video, we don't even need this. But anyway, when you are applying force here over this area of the piston, for example, okay, what happens? This water is coming out from all directions. So there are small holes in this glass flask, okay? So when you push, what happens? The water is coming out equally from all directions, from all holes. And you can mimic this kind of experiment with the plastic bag. So you fill plastic bag with the water first, and then make fine hole in it with the very fine needle, right? And then you start squeezing it. What happens? The water is gonna start shooting from those tiny holes, all tiny holes. And they're gonna be coming out with about the same speed, okay? So anyway, so what that means the pressure is distributed equally all side, everywhere, okay? And if you wanna make the measurements, actual measurements, you can do that. So you change the pressure here by squeezing this rubber ball. I don't know what that's called. You change the pressure here everywhere. What happens? It changes equally, okay? So inside the enclosed container, pressure changes equally everywhere. That's what it means, okay? So now, how is that related to our body, and how can we explain certain thing? For example, there is this condition called glaucoma. So in that case, what happens is our retina feels larger pressure. And retina is where the image is formed. So just like you have a screen, right? Nice straight screen. And there is an image on the screen. And now you let's say, distort that screen, what's going to happen? Image seems to be distorted. So similarly, when our retina gets pushed by that, the pressure, what happens is it gets distorted. And because of that, we see blurry image, distorted image, okay? And so why does that happen? To keep our, eye moist, there is source and sink of fluid. So sometimes what happens is the sink may get blocked. When sink gets blocked, what happens is there's going to be accumulation of more fluid. And there is already fluid inside here. So what happens is this pressure gets transmitted all the way down there and distorts the retina. Okay, so that's what's happening there. So pressure is being transmitted through that fluid equally all around there. And since this has a round shape there, it produces distortion, okay? So now, here what it is saying is the change in pressure. So when you apply pressure, you are changing pressure at that point. So change in pressure is equal everywhere, right? That's what we learned. That's the Pascal's law. So pressure can be written as force over area. We know that. So now let's look at this hydraulic lift. So we are applying force F1, and the area of the piston over there is A1. So the pressure over there is F1 over A1. So that's how much pressure we are changing by applying that pressure there, right? By applying this force in that area. So now what happens? There is fluid, means this pressure gets transmitted equally. So whatever pressure change occurs here, same amount of pressure change occurs over there as well. So change in pressure is same, but what happens is now the area is different. So because of that, force is going to be different. So area is different means force is going to be different. So now we can solve for force over there. Okay. So what happens? Now the force we get here, this lift force, for example, is related to the fraction of the area. So for example, if this area is 4 times A2 over A1 is 4, means the area A2 is 4 times larger than area A1. That means the force over here going to be 4 times larger than force we are applying. So you are multiplying the force by doing it, okay? So by making this area even bigger, let's say 10 times larger, you are making that force 10 times larger. It's directly related to the area, but sometimes you may be given a radius. So for that, you need to recall that area is square of the radius. So when you double the radius, what happens? The area becomes 4 times larger, right? So doubling radius you are making. So for example, let's say radius of this one is 1 centimeter and radius of this one is 2 centimeter. So you are doubling the radius. By doubling the radius, you are making area 4 times larger. So force is now 4 times larger, not just double, but 4 times. So remember, this is the fractional area, but sometimes you may be given radius. So you need to take account of that when you are given radius, okay? So that's how you multiply the force. So if you try to lift a truck, most likely you cannot. I cannot for sure, I know that, okay? But if you put that in hydraulic lift, And then what happens is maybe you can do it. So yes, there is this, there is motor that's pushing it down, but you may be able to do that if you have that kind of arrangement, okay? So depending on how much larger this area is, your force gets multiplied. So that means you can lift larger weight. Okay, so that's how the lift works. Hydraulic lift, okay? So it has a fluid. And probably you've been driving your car for a while, and if you go for some sort of oil change, then the car mechanic may say, okay, you may have to change your brake fluid as well. Huh? Is there fluid in the brake? There is, right? And so what happens is there is this foot pedal. So by making area larger here, it can multiply force. So just by applying small amount of force, you are applying larger force on the tire. I mean, rather than saying tire, maybe I should be saying these drums that holds the, like the spin of the tire. So it can slow down the spinning, okay? So that's how the way a brake works. So there is this fluid. So there is this hydraulic thing. Use of fluid is there, okay? So how does the pressure changes with depth? So we saw when there is really large height, what happens? Pressure change. We saw that in one of the video where, the barrel was being broken by applying small amount of liquid, but that liquid was filled in a very thin tube so that the height became so large that the pressure became larger, right? So here we can even compare it. So there is this, okay, hold on. Let's watch. For some reason, my mouse is not stopping the video and not playing the video.
You're on draw, sir.
Okay, so now, let's see if that works. Yeah. Ha. See, this one is going like this. Think about this water as a projectile. So if you start with larger speed, larger means it's going farther, right? This one not going that far, so it's just falling closer to this. So what's happening here? The depth or the height from this, or maybe I should go other way around. So depth here, height above this point here of this fluid is larger compared to this, and this one has the smallest one. So different height produces different pressure, and pressure increases with increase in depth or height. Okay, so that's what we are seeing there. So I see your hand, Robert.
So my question is this: is that why the water towers usually have extra bands at the bottom of the tower to deal with the increased pressure?
Yeah, maybe. I haven't noticed that, but of course the water tower is there. So it's a tower because we want larger pressure so that when we take shower in our home, turn on the faucet, it comes with larger speed, okay? But about the band, I'm not so much familiar with that, okay? But
Thank you for your response.
Yeah, I'm sorry I wasn't that much helpful on that, okay? So we can actually write down the equation for that, okay? So using the basic definition of pressure, which is force over area, force, so fluid is sitting there, so weight of the fluid gonna exert the force over area, right? So let's think about just a cylindrical column. It's easier to deal with cylinder, okay? So here, let's say pressure is P1 and the area is A and pressure is P1. And at different depth, pressure is different, right? We know that, and it's larger. So that means what happens is pressure times area is force, so that is force at that point, and this is force at that point, isn't it? So what we can do is now we can make free body diagram. So there is force due to pressure. So that's from the bottom. So that's P2A. And there is P1A pointing down. So I'm just replacing this object by, let's say, point here, right? And there is one more force, which is weight of the water over there. Okay, we cannot just ignore that. So that's going to be mg. So what we want is we want the relationship between pressure and this pressure. Pressure at different height. So what's the difference here? Difference in height between those 2 points, okay? So that's the relationship we want. And we can easily find that. So we know this thing is in equilibrium. So that means net force must be 0. That means I can write this as a positive by assuming up as a positive. P2A is positive. When I assume that, P1A gonna be negative, and mg also gonna be negative. That's the net force. And since this thing is in equilibrium, or here object of interest is cylindrical water column. So it's in equilibrium means net force is 0. So I'm factoring A out from these 2 terms. But before that, I'm moving this mg on this side. It becomes positive mg. And then I'm factoring A out and bringing that A down here. Okay, so that's that. So finding mass of this water not going to be that much practical. Okay, it's difficult. So what we're going to do is we're going to write this mass in terms of area. So how is mass of the water here is related to area? We know water has a particular density and area is related to volume. So density, volume, mass, they are related, right? So density is mass over volume, we learned. So that means mass is gonna be density times volume. So I can do that. So I replace this mass by volume and density, product of that, and everything else is there. So now I can write volume in terms of area. So see, the way I have chosen this object, cylindrical, I can write volume as area times this height. So let's do that. Or depth, if you like. Height or depth is just a matter of perception, right? So now what happens? The area cancels. We don't need to worry about area, okay? So it simply depends on density and depth. So if we know what fluid is there, we know the density. So for example, we know the density of water, we know the density of blood, right? We know the density of air, we know that. So as long as we know what fluid is there, we know the density. And G is constant. So that means the pressure difference is directly related to the depth. So pressure is directly related to the depth. So what happens here? If you know how deep you are from this pressure point, so this is P1 here. So how deep down you are from there, if you know that, you can tell the new pressure. It's going to be this pressure to begin with plus this one. So it's directly proportional to depth. Change in pressure is directly proportional to the depth. So pressure doubles when you go deep down, double depth, okay? That's what that is. So now think about atmosphere. We talk about atmospheric pressure, and we may say, okay, we have a 1 atmospheric pressure, which is around 10 to the power 5 Newton over a square meter or Pascal, right? At the beginning, we wrote this number. And of course, there is 1.03 or something like that, okay, times that. But we can say that is close to 1. So that's the atmospheric pressure. But is that the atmospheric pressure at Denver, in Denver? Is that the atmospheric pressure on top of mountain? What happens? As we go higher and higher, pressure changes. So we are being a mile-high city from the ocean. We have lower pressure. Higher we are from the ocean, lower the pressure. Okay, so those standard pressure is written for the sea level. Okay, higher we are, lower the pressure. So if you go to the mountain, we are at around 12,000 feet, right? And so pressure is even lower. If you go to the Mount Everest, pressure gets only about 1/3 of the pressure near the sea level. So you need oxygen tank because you cannot get enough enough oxygen from the atmosphere there. So you need oxygen tank to survive, to breathe, okay? So anyway, so that's the pressure dependence of the, depth or height dependence of pressure at 2 points. So now here is question related to, directly related to what we just learned, okay? So yes, my sketch is not that great. So there are openings, okay? So there are openings here, openings. And they are not open, but there is this opening here, okay? So now here is question, and you have a minute to answer this. Thirty more seconds. Oh, 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, what we got? So mostly C, but there are others as well. So if I'm thinking C as the correct answer, why? How do I justify that as a correct answer?
Well, since you said that it doesn't matter, the area doesn't matter, and they're all at the same height, and the distance between the bottom and the top is the same, I thought that they would all have the same pressure.
They have same pressure, right? They are sitting on atmospheric pressure. All of them are sitting at same pressure. That means height has to be same. Okay, yes, sounds good. So yes, C is correct answer in this case. So if you don't believe me, you can take a look at this picture here, and you see they are all level. So water is always, you know, it makes its own level always, right? It's always level, no matter how the, you know, the, let's say, shape of the container is. It doesn't depend on that. Okay. Looks like it's already past break time. So let's take break at this point. Okay. So I was a little bit away from here. Looks like there was some conversation about the pet was going on, and there is a question about like me, whether I have a pet or not. I like pets. One of my kid has asthma, so because of that, I cannot, you know, have pets just for safety reason. Okay, but anyway, yes. So I don't have pets. Okay. So now let's get back here. So yes, I'm opening this poll, and you have a minute to respond to this. P here means pressure. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly B. P1 is less. P2 and P3 are equal. So yes, that is correct answer. So don't get fooled by anything. It simply depends on height or depth from the original level, okay? So let's keep that in mind. So now, let's talk about barometer a little bit. So this equation that says, okay, pressure simply depends on height. Let's us to build a barometer or device, something like that, that can measure pressure in terms of height, okay? Larger height, larger pressure, smaller height, smaller pressure, and so on, right? So it helps us to build that. So what we want to do is we want to make this one 0. We want to make this one 0 so that pressure, whatever pressure it is, going to be directly proportional to H. We don't need to worry about it. So for that, what we do is we try to make this vacuum, no air. So here, this tube is filled with mercury, okay? And this is also mercury there. So you have a tube, you fill that tube with the mercury, and then when it is full, cover it with something. So since this is mercury, you want to be careful. So maybe you want to use globe or something like that, right? It's poisonous thingy, right? So what happens? You close it and you invert it, and then you insert inside the mercury and then remove your hand. By doing that, what we are doing is we are making sure that no air gets trapped inside this portion, okay? So it's kind of almost vacuum, okay? No air trapped here. That's what we want. So since there is no air trapped in this region, there is no other kind of fluid or something like that, we can say that point is like an empty vacuum, no pressure. Okay, so that's why P2 is 0, sorry, P1 is 0. And let's say pressure here is same as atmospheric pressure, because we are measuring the atmospheric pressure. So what happens, that pressure is pushing this fluid to this height, and that is given by this equation. Okay, so that's the pressure, and that is the height, how high this fluid or mercury here stand. Okay, so now how high it's gonna stand, gonna depend on pressure, right? So we can solve for height. And let's say if it is 1 atmospheric pressure at sea level, standard pressure, and then that's 1 atmospheric pressure. And this is density of mercury. And this is value of G. So this gives us height, and that is around 760 millimeter or 0.76 meter. Okay, if you were to convert that into inches, you can do that, and it becomes very close to 30 inches. So that's how high a mercury column stands, okay, in 1 atmospheric pressure of this value. So now, why are we using this poisonous mercury rather than using any other fluid, for example, water? Sometimes I wonder. Do you wonder?
I've got an idea.
Okay.
It's because it's so dense. Because it's so dense, you could measure the changes, like the mass changes, a lot easier on a smaller scale, and something that you could hold in your hand instead of something that might be as tall as a building.
So if this wasn't this much dense, like if this was water, then the height would be nearly the height of the tube we need would be 14 times longer, right? Or larger. So the barometer would be really tall. So yes, density has that role. So that's why we are using the largest density fluid we can find, okay? So what happens? That way we can have the barometer of about 1 meter length. If this was made up of water, for example, then it would be like 9 meter, 10 meter tall. We need to have that, you know, water can rise 10 meter tall, let's say. So that means you need very tall tube. And 10 meter gonna be 2 floors, not just 1 floor, okay? So you need 2-story house. I mean, 1 story is not gonna fit on that, okay? You need a lot of room. So it becomes impractical, okay? So yes, it's because of the density, and denser means it's heavier, okay? So yes, that's the reason. Now, do you guys watch Weather Channel?
Yes, I watched the Weather Channel.
Yeah. So, or it doesn't have to be exactly Weather Channel. So if you are watching local channels, and if there is news, they usually give you the weather update, right? So sometimes, not all the time, sometimes they may show you the pressure map, okay, pressure map. And they say, okay, the pressure is rising. So, or from tomorrow, pressure gonna be rising, it's gonna get a bit higher. So what's gonna happen? This storm gonna go away. No more storm tomorrow, no more snow tomorrow, okay? By just watching how the pressure is changing, you can tell whether they are going to be storm or not. Okay, so how do they do it? So the fluid always likes to flow from higher pressure region to lower pressure region. Okay, so what happens is if the pressure decreases in this area, for example, then the air molecules from the other area want to rush in this area. Just like when you have downhill, and if you let water flow downhill, what happens? It rushes, right? It runs through that downhill. So same idea, these air molecules are rushing towards us when there is lower pressure. So that's when the storm occurs. But as the pressure increases, what happens? Oh, the air molecules do not want to come this way, okay? So that's how it works, okay? So by looking at how pressure is changing, you can forecast the weather, okay? But yes, forecasting weather is very complicated phenomenon. Whether the pressure gonna change suddenly or not, that's a different thingy. But anyway, so that's how the weather versus pressure is related. And I think in the chat, looks like Robert summarized it very nicely, okay? And yes, of course, it is very complicated phenomenon. We'll talk about fluid dynamics later. So fluid dynamics is one of the most challenging problem to solve it properly. So now you can use blood pressure, or you can measure blood pressure, right? So you see there is this fluid and that rises and falls, but you can have these days, you can have the digital meters. Oh, that looks not so normal. 240 over 163, are those the pressure numbers? Definitely not good. Oh,
Yeah,
he needs hospitalization if that reading coming from her, okay? Anyway, so what happens? Blood is flowing through our, arteries and veins. So there is this fluid. So it's exerting pressure just like the air inside the tire is exerting pressure on the tire, right? So same idea. So there is fluid inside our body, so it's exerting pressure, okay? So now what happens? If the area changes, area becomes smaller, then pressure becomes larger, isn't it? Right? Pressure becomes larger, we know that. So for example, if you are like me who likes bit kind of fatty food and a lot of carbohydrate, then what happens? You may get a lot of triglyceride, and that may convert into fat and can make this area smaller. Okay, so when area becomes smaller, then you have now chronically high blood pressure. That's possible. One possibility is there, right? So now we have two kinds of, pressure, or two readings, I should say, low and high, right? So how does low and high comes in? Anybody likes to share that idea? Where do we get like 120 versus, let's say, 80, low and high? Oh, there is that. Heart. So heart is acting like a pump, right? Is that what happens? So I read one is the ventroids that's contracting, right? And one is the atriums or something like that. Okay, artery and vein and their path. So Robert is drawing something. Would you like to say something, Robert? Oh, I see your hand as well.
Oh yeah, I'm so sorry. I was just noting the rising action of both areas. There was a rising action on two different areas, and I was relating that to what Kristen said about the atrium and the ventricle pumping. Thank you.
Okay, I see. So basically, when heart is contracting versus relaxing, higher pressure versus lower pressure, mainly that's where it comes from. But yes, there can be a slight change. It's not going to be straight line. But anyway, perhaps you guys know better than I do about the this kind of body structure and so on. Okay. So now let's talk about how we can use this information, okay, to find density of object, okay. So again, back to the cylindrical, let's say cylindrical object there, okay. So why we are using that? Because it's easier to find the area, volume, and so on. But as we saw, the pressure did not depend on area or volume, so it doesn't matter what kind of shape you use. It does not depend on it, okay? So for the derivation purpose, what happens? It's easier when we use this because we know easily, we know how to find easily volume of this kind of thingy, right? So it's the same thingy, but in this case, what we are doing is looking at pressure here and pressure here, and we know there is a relationship between those pressure. So this pressure here is smaller than the pressure over there. So right now we are not talking about weight of this, the mg, we are not including that, but we're going to include that when we use the definition of pressure, okay? So if we put something inside, so for example, if you put your hand with the, the straight fingers or palm, something like this, try to push in the water. What happens? Water pushes you back up, right? So you see the resistance when you push on the water compared to when you push on the air, right? So why there is difference in pressure? Because of water versus, let's say, air or some different other fluids. We want to look at the relationship between pressure and density, okay? So here, the net force gonna be the difference in force between this and that, and we know force is larger, down we go because pressure is large. So same, larger pressure, same area means force gonna be larger. So I can write net force as the difference between these two forces. And this net force is called the buoyant force, okay? So what happens? When something is in a fluid, it experiences net upward force. That is the buoyant force. And here, since area being equal, that's the convenience of choosing nice shape here, regular shaped object. I can factor A out. And now I can make use of the fact that these two pressures are related, right? We know that this pressure difference is just related to height, so I can plug that in there. Okay, so that's going to give me this. So now there is height and there is area. Height and area, product of height and area for the cylinder is the volume. Okay. So now, this is volume, that's volume. That's density, and G is right there. I haven't done anything. So density is there, and volume I got by replacing these two products. So now here is the thing. Here is the thing. Sometimes it could be confusing. Right now, this object, the cylinder is totally inside fluid, right? It's immersed inside the fluid. But let's say if you were to put a wooden block in the water, let's say you push the wooden block inside the water, what's going to happen? It's going to come up to the surface, and part of it's going to be up and part of it going to be inside. Okay, so the observation shows that, and this is important information, here it says volume of the fluid, and here this was the object, right? And here I am assuming that volume of object is same as volume of fluid. So see, this h is the height of this object and a is the area of the cylinder, right? So this is the volume of the object, and I am assuming that that is same as volume of displaced fluid. So what happens is, let's say if you have a water in a cylinder, and if you put something inside cylinder, let's say some object inside the cylinder, water level rises. So change in water level is exactly same as the volume of the object. So you can actually use that method to measure the volume, right? So what happens? The volume of object gonna be same as volume of fluid that gets displaced when object takes the place of the part of the fluid. So anyway, so when it is totally totally immersed, it's equal. But if it is partially immersed there, so inside, so this part is inside, that part is outside. That means in that case, the volume of fluid displaced is going to be only this part, equal to this part, not whole volume of the object, okay? So let's keep that in mind. It's not always equal to the volume of whole object. It's equal only when whole object is inside the fluid. If it is partially, then it's going to be only the part of the volume that's inside the fluid. So let's keep that in mind. Okay, so now how much is net force? It depends on density of object. I should say density of fluid, not object here, okay? This is density of fluid. Remember here, that was this equation, this was the density of fluid. So now since we have object and fluid, what we are doing is we are differentiating it by writing F. Here, the subscript F means density of fluid, not the density of object that's inside the water. So for example, let's say wood is in the water, then fluid is the water, of course, and wood is the object. So in this equation, this is not the density of wood, it's the density of water we're talking about. Okay, so that's why I'm labeling it. I'm making it more specific to not to confuse with two different densities. We have object, we have fluid. Okay, so this is the density of fluid. So now, the buoyant force depends on density of fluid displaced, volume of the fluid displaced, and G. And actually, that means this is going to be the weight. Remember? I should say mass, and when we multiply that with G, that becomes the weight. So density is mass over volume, means mass is, so I can replace this by mass, right? So fluid displaced is equal to the weight of the object. Okay, so buoyant force is equal to weight of the displaced fluid, not the weight of the whole fluid here, no, only the fluid that's displaced. And how do we know that? Most of the time, we have to go back to this equation here. We may know how much the volume is and what's the density of fluid, okay? So most of the time for the buoyant force, we're going to be using this equation here, Okay. So if we know what fluid is it, you know the density. Now, if you know what's the volume of the object or part of the volume of the object that's inside the fluid, that means you know the volume of fluid displaced. So finding that information is a lot easier. Okay. So this is called Archimedes' principle, and Archimedes discovered this when he was in a lot of stress, as the story goes. So are you guys familiar with this eureka moment?
No, we're not.
Okay, so I invite you to search that in Google and learn about that. Okay, eureka moment and Archimedes. So I'm not a great storyteller, but there is nice story behind it. Okay. Yeah, it was about the bathhouse. That's right. The story is like he ran out of the bathtub without even, grabbing a towel. He was so excited when he discovered this thingy. Okay. So now with this, we can do a lot sorts of thingy, and here is video of not that high quality, but it gives the message.
To collect the displaced water, I've created this overflow apparatus, a tub with a spout. Filling the tub over the spout, we will let water run out until it stops.
Is what they're saying important?
The surface of the water is now level with the overflow spout. Before we start, let's weigh this wood block. It has a mass of 266 grams. Our overflow tub is ready for use. We have an empty cup on a scale positioned to catch and weigh the displaced water. The weight of the cup has been subtracted. When we lower our block into the water, displaced liquid starts flowing out the overflow tube. The scale is weighing this displaced liquid. After a few minutes, the flow slows and eventually stops. The scale indicates that the displaced liquid weighs 266 grams. Do you remember the weight of the wood block? It was also 266 grams. What happens if I add a weight to this floating block? Like this 126 gram stone. The wood block sinks further, displacing more water. Can you predict the weight of the water displaced by the stone? Did you get 126 grams? That's right. The additional weight of the stone caused the block to sink further, displacing a weight of water equal to the weight of the stone, 126 grams. Now to solve the horse problem. We have a rectangular barge measuring 300 centimeters by 200 centimeters, sitting in a freshwater lake. A horse jumps onto the barge, causing the barge to sink 12 centimeters. How much does the horse weigh? Like the stone sitting on the wood block, the horse has displaced water equal to its own weight. We need to calculate the weight of this displaced water. If you think you know how to do this, pause the video and do the math. The barge, before the horse is loaded, is sitting at this level. It has displaced water equal to its own weight. When the horse jumps aboard, the barge sinks another 12 centimeters. The volume of water displaced by the weight of the horse is a rectangular prism. 300 centimeters by 200 centimeters by 12 centimeters. The volume of a rectangular prism is length times width times height. That's 300 centimeters times 200 centimeters times 12 centimeters. This equals 720,000 cubic centimeters. This is the volume of the displaced water. Now we need to calculate its weight. Fresh water has a density of 1 gram per cubic centimeter. This means that 720,000 cubic centimeters of water weighs 720,000 grams. Let's change this to kilograms. 1 kilogram is 1,000 grams. This means the displaced water weighs 720 kilograms. The horse weighs 720 kilograms, the weight of the water it displaced.
Okay, so that's how you can weigh a horse. And of course, you can weigh yourself by just standing on that floating ice cube, but you need to know how much volume of that ice goes inside the water. So you need to do careful measurements. So once you know that change in volume, you multiply that volume by density of water. Volume times density is mass. So that's your mass in kilogram. If you are using density of water in kilogram per cubic meter, but if you use in gram per cubic centimeter, that's going to be in gram, okay? So yes, you need to know the, like somehow you need to be able to calculate the volume that's going inside the water. So maybe, if it is regular shaped iceberg, then it's going to be easier, okay? Otherwise, it's going to be a bit difficult. But it does not have to be on the iceberg. If you have, let's say, wood, remember? Big, thick plank of wood, you can let it float, rectangular wooden block, and then you stand on it. But it has to be large enough so that it doesn't sink all the way, okay? If it sinks inside the water, if it sinks all the way inside the water, or if it goes below the water surface level, then your math not gonna work. It has to be still on the surface or above the surface for this math to work, okay? So now here is a question for you. And you have a minute to answer this question. Okay, 30 more seconds, folks. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So this thing has a weight, mg, and there is tension, right? So tension is equal to mg. Did I make any mistake here?
Yeah, doesn't tension have something else in addition to it? Doesn't it have normal force somewhere?
Normal force, is it sitting on some surface?
Well, yeah, there's some water or some buoyancy. There's matter that it's sitting on at least.
Or you said buoyancy?
Yeah, there's matter that it's sitting on that's pushing it up.
Yeah, there is buoyant force. Yep, I missed that. So now, what's happening? Weight is balanced by these two forces, so weight must be larger than tension, right? Or tension must be smaller than mg.
Wait.
Or you can write equation, since this thing is in equilibrium, let's say T up as a positive. So what happens in this case is sum of forces along the y direction must be equal to 0, means T plus FB is equal to M, oh, hold on. I'm jumping here and there. So that means T is, move mg on the other side, it becomes positive. And also move FB on the other side, it becomes negative. See, so for example, 10 minus 2 is 8, right? So mg is bigger than T, or T is smaller than, and don't ask me where did I get those numbers. It can work with any number, okay, any numbers. Another way to look at it is now buoyant force is helping, right? So we don't need as much tension here. So if you try to lift somebody in the air, not so easy. But if you are in the swimming pool and that person is inside the water and you are lifting it, then it's going to be a lot easier. You don't need to use as much force. You are getting help from the buoyant force there. Okay, and buoyant force always acts upward. Okay. Oops. So our T was mg minus fb, right? So now the question is, if the cube has 4 centimeter long side, so this is cube, so 4 centimeter long, L is 4 centimeter. So maybe we want to convert that into meters. So that means volume of the object or cube is L cube. And since this cube is all the way inside, volume of fluid displaced also going to be equal to L cube. You see that? And what is the tension on the string? So why do I need this? Because I need buoyant force. Buoyant force is volume of fluid displaced, density of fluid times G. So that means it's going to be L cube, and then density of fluid displaced and G. So now I know kind of buoyant force. And how about mg? So see, the density is given. So mass is going to be volume of the object times density of the object. See, there is fluid versus object. So that's why I'm using the subscript here. So buoyant force, if I were to start from here, I can write that. And there is G as well. Volume of the fluid displaced, density of fluid displaced times G, right? And volume of object and volume of fluid displaced, they are same. L cube and G gonna be same as well. So what's remaining? Rho 0 minus rho F. This is volume of object, which is equal to volume of fluid displaced. So now we know everything. So this being water, density of fluid gonna be 1000 kilogram over meter cube. Okay, so that's going to be the tension once you plug in numbers and get the answer, okay? Oh, sorry, I kind of looks like I went 4 minutes over the class time. Sorry about that, folks.
It was engaging. Have a great day, Professor Tungana.
Hey, you too.